recording. Okay. So let me now share the screen. And consequently, let me share the presentation. Okay, do you see my screen?
Yes, I can see.
Okay, perfect.
Yes, Professor, it's visible.
Okay, so let us forget about that. Actually, the lecture was, I took this first page from a lecture which I gave some time ago, some months ago, being in Italy. And the title was, as you can see, How to Successfully Analyze NMR Relaxometry Data in 5 Steps. Well, maybe the title is not the best one. However, the lecture starts from the beginning because, of course, the first step is to understand what NMR is, yeah? Otherwise, you cannot analyze your data in 5, 50, or even 1 million steps. The first step is always the same, to understand what NMR is. And here is this picture, which you know very, very, very well. And actually, this picture shows a box in which there is a lot of water molecules. As many as I, have the fantasy to grow, to put there, still to make this presentation like with clear. So you have a glass of water. So you have a box with a lot of water molecules. I'm risking at this moment because I fear that you might start thinking that NMR is about water, and then one must have water to perform NMR. Actually, it's not true. However, water is the simplest molecule and a very common molecule, and somehow this is a good example. So everybody knows that a water molecule includes 1 oxygen atom and 2 hydrogen atoms. I think so far this is simple. There's also a lot of other molecules in the world which include hydrogen atoms. So let us forget about water. Let us focus at this moment on hydrogen. Then I'm risking that you will think that actually to perform NMR, one necessarily must have hydrogen in your sample, and this is also not true. However, let us stick for today for hydrogen. So, in fact, you have a lot of hydrogen atoms in your box. The hydrogen atoms belong to water molecules, but they must always belong to something. Then, what one can say about the hydrogen atom? It includes nucleus, and this is actually a proton, and 1 electron. Yeah, this is the simplest atom. Let us forget about the electron. Electron can be important, it will be important for electron spin resonance, which we also have in our lab. But at this moment, we are dealing with nuclear spin resonance, so we focus on the nucleus. And now the story starts. Because protons have magnetic moments. At this moment, 2 questions arise. First, what a magnetic moment is. Second, why protons have magnetic moments. Regarding the first question, what a magnetic moment is. One can never really explain everything. For sure, everybody have seen, I don't know, magnets attached to freezer. Yeah, this is a kind of obvious thing. However, if you really like, Karim is asking if the meeting is going on. Okay, if you really want like to understand something about magnetism and magnetic moments, not on the level of, something which you bring from vacation and attach to fridge. And this is really important that you do understand it on a somewhat different level, because after all, you perform magnetic resonance. I would really recommend that you try to read. I mean, I'm not able to explain everything, and this is somehow on the really, really level of basic physics. After all, Earth has magnetic poles and so on and so on. So this is like a knowledge which I would propose, that you try to learn a little bit in case the concept of magnetism is still not clear. We can discuss it, but at this moment, there will be hundreds of things like this. So let us at this moment assume that everybody knows what a magnetic moment is. Then why protons have a magnetic moment? I don't know. And nobody in the world knows. It is like you could ask why objects have mass. This is how the world is made. And actually, I keep saying that physics explains how, but does not explain why. It's end of the story. I do not know why protons have magnetic moments, and nobody will answer to this question. However, there's even more tricky. The magnetic moments can be oriented only parallel or anti-parallel to the applied magnetic field. I mean, if there is no magnetic field, you take a glass of water and you put it on a table. The magnetic moments are distributed, oriented completely chaotically. All possible directions are allowed. However, when you apply an external magnetic field, and this is what we do in our experiments, then there are only two possible orientations, parallel and anti-parallel to the magnetic field. You can again ask why. Again, I do not know. But look, we are attached to the concept of freedom, yeah? We can think that we can do whatever we like. So I would put it in this way. How many times in your life you can say good morning, for instance? You can start now. Good morning, good morning, good morning, good morning, till the end of my life. Actually, the thing will be that, well, the lifespan will be not very long, because after all, I have to eat, and it's not very polite eating and talking at the same time. So, for instance, yeah, this is already a kind of limitation. But being serious, of course, it's not like I can say it 100 times. I can say it 102 times, yeah, and so on. But I can hardly say it 100.12785 times, yeah? I say it or I do not say it. Then you can say, no, well, this is a kind of stupid example. I say, not necessarily, but okay. Because after all, there are things which go continuously. After all, I can drink as much water as I like. Well, this is also a matter of debate. However, I would answer this question. Try to drink less than 1 molecule of water. I wish you luck. But then you will answer me, come on, not with this accuracy. Nobody cares about 1 molecule. The thing is that we do not care about this kind of restrictions, that not everything is allowed. Because this is a very small, tiny amount, I would say, quant of things which are not allowed. It's like, you pay 1 million euro for something and somebody is asking you whether it can be with accuracy of 1 cent. You do not care, yeah? Because we live in the macroscopic, not quantum world, so it does not mean that we do not observe restrictions of quantum mechanics, of quantum physics. It's only that they are not important for us, everything considering, yeah? But when we deal with things on the atomic level, this becomes of essence. So there are only two possible orientations, parallel or antiparallel. End of story, nothing between. Never, ever. No, okay. But then you can ask me next question. No, okay, but so they go like 50-50 or what? And what decides which one is up, which one is down? Regarding the second question, nothing and nobody, because the first thing is that you cannot distinguish them. You cannot say the first one is up and the, I don't know, 17 one is down. They are all identical, so the questions does not apply. The second thing is whether they go like up, down, 50-50. No. One orientation is preferred. And here, slowly, we are touching the level of quantum physics. Even if I would tell you at the beginning that you will become specialist in quantum physics, you will say never. But you can see that we are approaching the area of quantum physics. How many up, how many down? Okay, you are sitting at home probably, me also. It's very cold outside, actually. This is another area. I somehow think that regarding quantum physics in Olsztyn, they can be very cold or extremely cold, and there are those two quantum states. However, coming back to our problem, if you would attend something in person, and there will be a room and finite number of chairs, everybody wants to sit because it requires literally, in terms of physics, less energy. So sitting is a quantum state of a lower energy. Staying is a quantum state of a higher energy. And everybody and everything in the world tends to reach minimum of energy. This is the next fundamental rule of world. So what will happen? First, the orientation which is associated with a lower energy will be taken. And it does not matter which one it is. I never remember, and it is really of no importance. The crucial thing is that the numbers of protons, the orientations with all the magnetic moments oriented parallel and anti-parallel to the magnetic field are different. There's a difference. Because the orientation, which is associated with a lower energy level, is preferred. Actually, when we are talking about energy levels, we are approaching the concept of a quantum state, because I can say it in terms of quantum mechanics. Instead of saying there are only two orientations allowed, because this is like, to give you a kind of picture to play. But there's no such a thing like orientation. In the quantum world, there are just spin quantum numbers describing quantum states. But instead of just saying that there are two possible orientations, I can say there are two quantum states available. One is of lower energy, one is of higher energy, and the one of lower energy is, of course, more populated. So we associate it with the orientation of the magnetic moment, but this is much more complicated, just, like arrows which change orientation. Please, under no circumstances, do not imagine protons like spheres with arrows rotating or something like this. This is, only for the peace of our mind, because after all, the human ability to imagine things is limited, so we try to adjust this quantum conception to our world. However, okay, we have those two possibilities. Then I hope that you heard about something what is called Boltzmann distribution. If not, I strongly advise you to read, although it includes exponential function, which is maybe another story, and this is related to next lecture that we are going to have. But it also shows that everything in the world is about mathematics. There's no science without mathematics. Whatever you do, you can classify butterflies, but even then you need to count. Any kind of science is just absolutely and intrinsically related to the concept of mathematics. This is how our brain works, and you can refer here to biology. Even if you take a child and two children, and one of them gets less sweets than the second one. They really do not know how higher mathematics, but they will protest. So the concept of numbers is just impregnated in our brain, and this is the way how people think, and there's no way to escape from this. So, okay, the so-called Boltzmann distribution describes the probability of a state being taken if there's a certain energy of the state and there's a certain temperature. Here we also refer to temperature, to absolute temperature. It means temperature in the Kelvin scale. It's like temperature in Kelvin is temperature in Celsius plus 273. Fahrenheit, I do not remember. However, what is so special about this absolute scale is that it is related to physics. If there is no energy, no motion in the system, everything is frozen. It's like 0K. Therefore, there are no negative temperatures in the Kelvin scale. However, so this kind of knowledge is needed even to understand the concept that higher energy levels are more populated. In end effect, as a difference between the number of magnetic moments up and down, saying in a kind of naive way, I get something what we call magnetization. Because I have, for instance, I don't know, 1 million up, 1 million 1,000 down. The difference is 1,000, yeah? And they sum up, and I get a larger magnetic moment, which I am able, to detect, observe, and so on. Then imagine that there is no magnetic field, like in the beginning, and then I apply a magnetic field. It is, of course, obvious that higher magnetic field means, larger energy difference between those two states. It's like comparable to the situation that everybody can see it, but there are, better and worse seats, yeah? More comfortable and less comfortable. Okay, the fight to take the best seats is not so strong, because after all, okay, I can still sit and it is not so bad, yeah? But if it is like deciding between sitting and staying, the fight will be much stronger. So the difference between the populations of those two energy levels depends on the magnetic field. It's actually proportional to the magnetic field. Stronger magnetic field, stronger difference, larger difference. And Eventually, this means that when you apply the magnetic field, the system starts a certain process, namely from the chaotic distribution of the magnetic moment, you will see like the order is created, yeah? Some of them orient parallel, some of them anti-parallel. We already said that the question which one does not make sense. And eventually, following this Boltzmann distribution, this Boltzmann law, will reach a state in which, yeah, according to the Boltzmann law, actually this specific number of magnetic moments up and down is reached. So the system reached equilibrium. The magnetization has been built. Relaxation is actually nothing else like reaching equilibrium in a specific conditions. So in this case, relaxation is just reaching the magnetization resulting from the difference in the populations of those two energy levels, as expected by the Boltzmann distribution. And this process is called relaxation, as I said. However, it takes some time. And this time is called spin lattice relaxation time. Why lattice we will learn later. You can ask how long it will take. Well, it depends on many factors and can be extremely short on a level of microseconds. For water, it is like more than 2 seconds, between 2 and 2.5 seconds, which gives you a scale, yeah? This is the longest relaxation time, actually. And attention, the magnetization is built following an exponential function, which shows again that math is of essence. Okay, so after those short or long explanation, let us go point by point and tell me if you do not agree with some of the points, okay? It does not matter how many slides we'll go today through. It can be, if we go through 5, it is also fine. It's just important that you understand the principles. So we agreed that that nuclei of hydrogen atoms possess magnetic moments. Nobody knows why. In a magnetic field, the magnetic moments can take only 2 orientations, parallel or anti-parallel to the magnetic field. Okay. More magnetic moments is oriented parallel than anti-parallel. Maybe I suppose that at that time when I was preparing this slide, I just checked this, but this is of no relevance. This leads to a larger magnetic moment of the sample. I suppose that here we agree as well, because the large magnetic moment stems from the difference between the populations of those two energy levels. Then there is the point 4, which is very, very problematic. The reorientation of the magnetic moments requires time and energy. First, I hate to use the word reorientation, because this brings us close to this concept of sphere with attached arrow orienting, and this is an entirely misconception. However, there are no better words, yeah? So somehow try to be in this, how to say, strange quantum state. So from one side, you understand that this is nonsense from the point of view of science. This is like, talking to children, like, I don't know. One should not use this kind of description, explain things. However, it helps. What one should say it is like that reaching the state in which the populations of those two energy levels and the populations are actually with specific magnetic quantum numbers, not really, one should not think, be attached to the term orientation, but whatever. This process of inserting this kind of order in the system takes time and energy. Actually, time we already agreed. And we said that the time needed for the magnetic moments to reach the distribution of the orientations appropriate for a given magnetic field is called relaxation time. This we also said. But why energy? This is less clear. Let us stay with the simple pictures that some of the magnetic moments are up. So the parallel orientation is associated with lower energy, looking at point 3. The anti-parallel orientation is associated with higher energy. And now assume that I change the magnetic field. I reduce it or I increase it. This is, after all, what we are doing in NMR relaxometry. We change the magnetic field. What happens then? Well, the system should reach the new equilibrium following the Boltzmann distribution. So if I reduce the magnetic field, the difference between the populations of those two energy levels should become lower and the magnetization should become smaller. If I increase the magnetic field, the difference should become larger and the magnetization gets higher. But to go from a lower state to higher state, I must get energy from someone. Also in the opposite direction, to go from higher state to lower state, I must somehow release the energy. And there must be something what is ready to take the energy, to absorb it. So therefore, this process is associated with energy. Then, with what the system actually exchanges the energy? With other molecules. With other molecules and ions in the surrounding. Because after all, we have a glass of water. Yeah, including many molecules. And the molecular surrounding is called lattice. Therefore, this process is called spin lattice relaxation because it involves interactions with other objects, which we call lattice. It's actually a historical story because, it started probably with crystal lattice and some phonon transitions and so on. And then somehow this concept survived, which can now be somewhat, I don't know, not clear at the beginning. But then you can say, no, okay, but what the lattice, what the molecules, what kind of energy they have? Because they move. And now you can ask next question, why molecules, objects move? Here again, I can refer you to high school physics and the concept of temperature, yeah? For sure you learned that temperature, in the Kelvin scale at least, is the measure of the kinetic energy of molecules. So only at 0 K, there's no motion. Otherwise, molecules are in constant motion. This is also something, I didn't realize. It was a moment when I was explaining something, and then somebody asked me a question. But this glass of water is not shaking. So what do you mean that the water is in motion? I do not mean microscopic motion, like you take a glass of water from this place to that place. By motion, I mean motion on the molecular level. If by miracle, and this is actually what we investigate, this kind of motion is we investigate applying NMR relaxometry. If I still take the glass of water and by miracle I would be able to label one of the molecules painted in green and another one in red, does not matter that this is impossible. Actually, there's another. One can always, and maybe not always, but in many cases, one applies something what is called isotope substitution. For instance, it places, attaches some paramagnetic molecules, or just coming back to the isotope substitution, replaces, for instance, one H by 2D or something like that, and then there are methods to follow them. But putting this aside, let's imagine that by miracle I can label them. And I look at one of them. It will be moving stochastically in all possible directions, forth and back like crazy in the whole glass. And the same applies for any other molecules. However, as we do not distinguish them, for us nothing is happening. It's like, I, for instance, put, I don't know, a green ball on a table, and you will be coming to my room every 1 minute, for instance. And I will be staying and replacing constantly this ball by another ball of the same color, size, and so on. You do not see it. Yeah, from your perspective, this picture is constant. But it is not. So this is when one is just a moment. This is when one says something about translation and rotation dynamics. I will come back to this in a moment, but this was question, yeah? Because somebody raised hand.
Yes, Professor.
Hello?
Professor, what I wanted to ask is that in case if there is only water in your sample and there are no other molecules to which they can dissipate their energy, then how would we'll get the spin lattice reaction in it?
Yeah, this is a good question, and again, quite unexpected one. Before I answer to the question, yeah, because it didn't come to my mind that one can see this as a problem. But okay, first, before I explain this, let me explain about translation diffusion because it's very much related to this, yeah? When we say about translation diffusion, the typical picture which you have in mind is that, well, let's say, there is something smelly in one corner of a room. Yeah, for instance, we open fridge with our cheese samples stored there for some time. And then after some time, people sitting in another corner became aware of this. Yeah, this is how we understand diffusion. Then, this is also like those demonstration in elementary school that you take a glass of something, then you like put some color liquid into it, and you observe like the color moves. This is not a diffusion in our sense. Okay, this is a kind of mass transport. This is first thing. Because after all, the molecules are moved from one point to another. But one can also say, if one sticks to the concept of diffusion, that this is diffusion in a gradient. Yeah. So it is like a mixture of two kinds of molecules, and they are like separated. And at the beginning, in one place, there is more of one kind of the molecules, less of the other. And then somehow, it is like we can have also two boxes, yeah? In one part, we have one thing, and another part, another. And then we take out this wall, which was like separating them, and they start to mix, yeah? This is also another kind of school example. This is diffusion in a gradient, in the concentration gradient. In one place concentration was higher, in another place concentration is lower, and the system tries to equilibrate the concentration. Eventually, of course, if there are molecules 1 and molecules 2, if molecule 1 moves from its place, then the place becomes empty, so molecule 2 moves to its place, and so on. Yeah, like motion in two directions. This is a completely different process. Forget about it. It's a nice phenomenon, but it is not what the science in our case is about. From our perspective, if I take a glass of water, and now I come to your question, and this is just only water, nothing else, collection of identical molecules. From my perspective, and well, not mine, from the perspective of science, let's say, the molecules perform diffusion. Because they are in constant movement. They perform something what is called Brownian motion, another very fundamental element of science. And they constantly move in all possible directions. I don't know how to explain that because, well, this will be like pretty stupid example. But imagine that you have like a room with very many people, and for whatever reason, all the people seem to be identical to you because I don't know, they wear something and it is dark or whatever. Let us put this aside. For whatever reason, you cannot distinguish between those people. Yeah. And everybody moves in completely chaotic way with a certain speed. The people bump in each other, jump back, start in another direction, and so on. But they are in constant motion. Absolutely, and this motion is completely stochastic. Those people perform translation diffusion because they change their position. If I, insert a kind of coordinate frame, X, Y, Z, yeah, each person changes their position in time. Of course, if I look at this process on a long time perspective, the average displacement of every person will be 0. Because after all, the probability that the person steps in right is the same like the person steps in left. And so on, yeah? And this applies to all possible directions. From the very definition of stochastic motion, All directions have the same probability. So if I look at the movement of a person for a short time, okay, this person can make 5 steps to the left and only 1 step to the right. It can happen. There is a certain probability that it will be like this, yeah? Like in the way, you just throw your corn and there are those 2 sides, and in principle it can happen that 5 times is side 1, 1 time is side 2, yeah? However, in the long run, you expect 50-50. So the same is here. From a long time perspective, much longer than the speed with which the people move, the average displacement of everybody is 0. However, the people are in constant motion. And this is the essence of diffusion process. And this is the essence which determines, I would say, life, chemical reactions, biological processes, and so on. This is this kind of movement. What determines life, for instance, is protein dynamics, and structure, but the dynamics in the sense as we are describing now. Not that you put the protein somewhere and they diffuse, or I don't know what, the concentration equilibrates. If you take, for instance, tissue, yeah, it has a structure. It's not frozen, will be in 1K, 0K. And the molecules building our body are in constant motion. If you want to bring it to a level more close to biology, I think, I don't know, microscope with bacteria, yeah? They move stochastically in all possible directions. This is the motion which determines life. And this is the motion which we investigate. Now coming back to your question, what happens if we have only water molecules in the glass? Well, first we have to explain how the molecules communicate. Yeah? Because what does it mean that energy is transferred or taken? There must be a kind of connection. Yeah, it's not like I don't know what. After all, it's not radiation or something, yeah? So how do the molecules communicate? Because I artificially select one hydrogen atom, I say that it has a magnetic moment, and the magnetic moment has 2 orientations, and somehow this particular hydrogen atoms, this particular proton being the nucleus of the hydrogen atom, this hydrogen atom feels the need to exchange energy. With what? With other protons in the surrounding. Does not matter to what molecules they belong. They do not need to belong to different molecules. But the question is, what is the communication channel?
The way they bond.
How they see each other. Bond how? After all, there is no string between them. Yeah, so this is just a thing. Because if you make the analogy, with the group of people who move in all possible directions, let's assume that one of the persons, I don't know, wants to sit. So what? Nobody cares. Yeah? Or maybe, sorry for this whole example, and I don't know how to, it's stupid example actually, sorry. But if this person is actually sitting and didn't have breakfast and does not have the energy to stand up, it's not like miracle happen, yeah? Okay, another person had breakfast and has the potential to sit and stand many, many times. But so what? You can say at this moment, no, okay, but this person who is strong can help the other person, yeah? Yeah, but must you know? Raise hands, touch this person, bring, transfer energy, yeah? And how to say then the so-called bonding, the contact is how to say by physical contact, yeah? By applying force in terms of physics and doing this.
Yes.
So, but we have to define something like that between molecules, not really between molecules, but between protons, between the magnetic moments. Because otherwise there is no way to transfer energy in any direction. Let me, so this will be the next, I will explain this in a moment. Let me only finish this story that I said here that the energy is taken from molecular motion, for instance, such as translation and rotation dynamics, and this is not clear at this moment. I mean, we spoke about translation. About rotation, not yet. And then is this enigmatic statement that NMR relaxometry provides information about the time scale and mechanics of molecular motion. This is not clear. We'll come back to it in a moment when I explain this, because this is exactly your question. So let me come back again to the point. We have this random distribution of magnetic moments with no magnetic field. Then we apply magnetic field, and we have this order determined by the Boltzmann rule. Some of them are up, some of them are down. And then, as I said, I change the magnetic field and I want to change those populations. And what will happen now? If the magnetic moments have the ability to interact with external magnetic field, they also have the ability to interact with each other. If a fridge magnet has the ability to interact with the fridge, two magnets have also the ability to interact with each other. And this is what is happening at this moment. Magnetic moments of protons interact not only with the external magnetic field, which is which creates very, very big magnetic moment by itself. They also interact with the magnetic moments, in other words, magnetic fields, generated by the magnetic moments of the neighboring protons. So if you take, for instance, water molecule, it's like, again, high school physics, when you take two magnetic dipoles, yeah? For instance, there were like those old, like North Pole and South Pole, those red and blue, magnets, yeah? And how they reorient and so on. You had even, this like you have some small amounts of iron, some tiny elements like powder and orientation in magnetic field and so on. All those stories, as I said, high school exercises. However, what is here, one can say it again in this way. The magnetic moments of protons interact with each other. In the same way as they interact with the external magnetic field. You can talk about intramolecular interaction if you, for instance, if your molecule includes more hydrogen atoms, consequently more protons. But as I said, it's not only about hydrogen and NMR concepts, also other nuclei, but I think it's complicated enough at this level. But also between protons belonging to hydrogen atoms of different water molecules. Because we have a lot of water molecules. And the magnetic dipole-dipole interactions is just the way how they touch each other and how they transfer energy. So for instance, if I imagine, that I focus on one of them, it interacts with the whole surrounding, the lattice, yeah? The magnetic dipole-dipole interaction of this particular proton, the magnetic moment of this particular proton with magnetic moments with all possible protons in the surrounding. Of course, if they are more distant, the interaction is weaker. But let us now come to the point that the molecules are in constant movement. So, in contrast to interactions with the magnetic field, the external magnetic field, which is applied and end of story, it does not fluctuate in time. The dipole-dipole interactions between magnetic moments of different protons from the same and from different molecules stochastically fluctuate in time because the molecules move. This is what we discussed a moment ago, yeah? If I hypothetically focus only on two molecules, then the molecules will change relative orientation, will change distance, because everyone moves completely stochastically. It's like, I give a string to two people, keep the string in your hands, and then now move above of you completely stochastically, yeah? The orientation of the line with respect to whatever, I have to choose a reference system, but the orientation, as long as the length, which somehow represents the distance between those two persons, will be constantly changing in time. So the same is happening here. Now is the question, how fast? Of course, here one should again insert a kind of quantity which characterizes the speed with the movement, yeah, how fast the motion takes place. All the time we are talking about things on a molecular level. And here one, again, one needs to introduce a kind of definition. This is again, again, we need basic mathematics. Because for instance, when you drive a car, yeah, and somebody wants to know how fast you move, you do not answer just 110. It means nothing. The measure of how fast is 110 kilometers per hour, yeah? If you are able to refer this to a kind of time frame, yeah, this will give you information about the speed of the car. You have to compare the distance which, I don't know, two drivers were able to make during the same time. Yeah, otherwise this does not make sense. It requires a kind of normalization, and here the time is the normalization that it refers to 1 hour. The same is if you try to describe how fast molecules move, you introduce two quantities. One of them is translation diffusion coefficient for translation diffusion. And what translation diffusion is, we already discussed. The second quantity is called rotational correlation time, and it describes how fast molecules rotate. We didn't talk much about the rotation dynamics, and this can be again a kind of confusion. But imagine again those people in a room which move in all possible directions, and there's a lot of people, so they jump into each other all the time, yeah? With quite a lot of force. What will happen? If you run into another person and you are hit with this force, very likely it's not you are hit and you just step back. You will also rotate somehow, yeah? Then somebody else will hit you from other side. And I would just say that if at the time zero you are facing window, assuming that there's a window in this room, after many, many collisions like that, very likely you will face the opposite wall. And this can happen even if you do not perform translation motion. Even if you are glued to one place, you still will rotate around your axis. And in reality, you do both things. The same do molecules. So one should not imagine rotation dynamics like, I don't know, I have, like insect pinned to a wall, and it rotates clockwise and anti-clockwise. It's not rotation dynamics. It's not in this sense. This is again stochastic process. Just like the translation diffusion is changing position by a small step, very, 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 very small step when we reach the level of derivatives and differentiation and so on, but let's say very, very small step, then it means here you change your orientation, the molecule changes its orientation by a very small angle. And then this happens stochastically, and the question is how fast. And there's this rotational correlation time, and then the diffusion coefficient, and they always refer to something, So you can look up the diffusion coefficients, but they are related with, as I said, for instance, for translation diffusion, as the probability that you make step to the left and to the right is the same. So if you think a little bit in terms of mathematics and you imagine x-axis and that you are staying at zero and steps in the right are positive, steps in the left are negative, if I would count your effective displacement, the displacement will be zero, yeah? Because in long term, you will take the same number of steps in the positive direction like in the negative. But if I decide not to care about the sign, so for instance, instead of taking the displacement, I take square of the displacement, because 1 power 2 is 1, minus 1 power 2 is also 1, yeah? I really can't have absolute movement. And in this sense, if, for instance, I sum up all the squares of the displacement and divide by time, if the number is larger, it means the motion was faster. So this is a kind of reference. Analogous reference, it includes somewhere factor pi, I do not remember, is made for rotation motion. So somehow the quantities like translation diffusion coefficient and rotational correlation time are well defined. It's like, for instance, after a long time, after what time the square of the effective rotation angle is pi or pi half or something like this. I would need to look up. So but what I want to say, they're really a measure of the speed of the motion. And now the magnetic dipole coupling between neighboring protons fluctuate in time. And there are two factors determining the fluctuations: the time scale of the motion, faster, slower, and the mechanism of the motion. It depends whether there is translation diffusion or rotation motion, or we call it rotation diffusion, or any kind of vibrations, or any kind of collective motion. The mechanism of the motion matters. And now the relaxation time, as it is written here, describes how much time is needed let me avoid the word orientation, for reaching the right Boltzmann distribution of the magnetic moments. And the efficiency of this process, I mean, if the process is not very efficient, the time is like longer, yeah? Efficiency of this process depends on the amplitude of the dipole-dipole coupling, of the strength of this dipole-dipole coupling, which is a kind of common sense, yeah? Because the ability to exchange energy depends on how strong the coupling is. Then it depends on the time scale of the motion, the time scale on which the dipole-dipole interactions fluctuate, saying it scientifically. So it depends on the so-called correlation time or translation diffusion coefficient. And the third factor, which is not clear to you at this moment, is the mechanism of the motion. So even if the time scale of the motion is pretty much the same, but the mechanism of the motion is different, then the efficiency of the spin transitions and of the transitions of the magnetic moment, let us not talk about spins at this moment, it will be such a time, is different. Let me only check something. Okay. So therefore, what is written here, analyzing the relaxation times or the reciprocal values, relaxation rates, you get information about the time scale and mechanism of molecular motion. And before we proceed further, let us take 2 minutes break and think whether you have questions. If you don't, we'll build together this relaxation scenario, but I suppose you might have.
Professor, I wanted to ask that the parallel and anti-parallel moments of molecules that we spoke about upon providing magnetic field, is it important to have both at the same time, or and if so, what is their significance? Like, the difference between the parallel and anti-parallel moments, does it provide magnetization, or is it something which is
Sorry,
possible?
I didn't get it. What do you mean at the same time?
So you said that when we provide magnetic field, there are two possible directions,
Yes.
orientations, which are possible. Either it can be parallel or anti-parallel, but is it possible to have parallel and anti-parallel at the same time?
Well, I would ask you now the question whether you can sit and stay at the same time.
No,
The answer will be obvious. You
but
can
but
take.
there are a large number of molecules, and like each different molecule, if treated as a person, then like some of them can sit and some of them can stand.
But this is then a different question that we are talking about. Therefore, I said that we have a class of water molecules with very, 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 very many water molecules. And we cannot distinguish them. So you cannot say like, this is molecule one, and you know the magnetic moment of this left proton, yeah, it's up, and this of the right is down. And this is molecule two, and both of them are up, or something like this, because we absolutely cannot distinguish between them. Yeah. But
But can we take the cumulative effect of the entire glass? Like if we say that there are 210 molecules, out of which 100 are sitting, and let's say 100 are parallel and 110 are anti-parallel.
this is exactly what we are doing. Therefore, for instance, from practical, point of view, people will ask you how much of the compound which you investigate you need for your experiment. And then you need to provide a kind of estimation. Then the person will start complaining. You said 1 milliliter. Come on, I have only 0.5. Yeah, because it's expensive. Then you ask the question, but what is the composition of this thing? How many hydrogen atoms per unit volume you have? Because after all, it's not only about the volume, it's about how many hydrogen atoms, how many protons per unit volume you have. And if the person says, a command is heavily deuterated, I have only, well, not much, because people usually do not avoid giving numbers. Then you say, but well, so this is, I will have to, the signal will be too weak. I will not perform the experiment. Because you must have sufficiently large magnetic moment for the electronics to be able, to measure what is happening with it. For this purpose, you must have sufficient number of protons, so the difference between the number up and number down is sufficiently large, so the net magnetization resulting from this difference is sufficiently large. But you will be never able to say this one is up or that one is down. I mean, it's on the level of Nobel Prize, actually, that there were, like attempts to detect signal from a single molecule by enhancing the signal gaining magnetization from electrons. This was actually not successful, in fact. But of course, people would dream to say, this is my molecule, and for this molecule, it is like it is.
Actually, this was what I was trying to understand, that these two moments of molecules like parallel and anti-parallel, what is the importance of that? But now I got the answer that they are important to generate magnetization, which you can detect through your
Yes.
electron.
Yes, exactly. However, the dream, to identify such things for a single molecule is like the dream of quantum physics, yeah. But this is also related also to the This is like going into the popular science, but for instance, this Heisenberg rule. Maybe you heard that you are not able to determine position and velocity at the same time. Or in this kind of popular word saying that if you try to look at something, this thing already changes its state because you perturbed by looking, because you must have means to look. So you somehow added new element to the system, whatever it is, and the system or the original one changed its quantum state. So it's like we can never see things. End of story. It seems so. It's like, why we do not travel in time. Yeah. We can
Yeah, you're right.
go into
Right.
that. Yeah. But this is, the power is in the number, let's say. You must have many of them for this purpose. Is there more questions? In the meantime, okay. Let me then continue. So I think this will be the last slide for today, but it will take us some time. Then next week we can proceed further. So for a while, we are taking a sample which includes atoms, the nuclei of which possess a magnetic moment. And this is the first surprise that protons, 1H nuclei, are only example. You see here also other nuclei. For instance, nitrogen is very often present in biological samples. The nuclei of which are atoms, the nuclei of which have also magnetic moments. Because proton has a magnetic moment, and depending on the composition of the nucleus and some quantum physics rules, the magnetic moments of the protons which build the nucleus sum up in different ways, and consequently, some other nuclei also have magnetic moments. And they can also be used for NMR. So you already learned something. Then we apply a magnetic field. This we already were there. The magnetic moments orient parallel or anti-parallel to the magnetic field, provided the spin is 1/2. And here we are reaching the point of a spin. Spin quantum number is just, one could say, artificial number attached to proton. But in this sense, everything is artificial number. The concept of time, the concept of mass, the concept of distance, the concept of color, for instance, that saying that something is blue, something is yellow, is also artificial number. Yeah, artificial quantity. The thing is that people try to explain how our world works, try to explain a lot of effects, and they build physical theories. And the theories survive the experimental verification or not. At this moment, it will really shake the world if you start doubting in something what is called spin. Namely, as we said, protons have magnetic moments. Magnetic moments are always associated with something which is called spin quantum number. And the fact that if you apply a magnetic moment, if you apply a magnetic field, for the magnetic moment of protons, there are only two possible orientations. It implies that the so-called spin quantum number of proton is 1/2. Why? Well, let me take as example. If you take, for instance, nitrogen 14, there is also nitrogen 15, but if you take nitrogen 14, there are three possible orientations of the magnetic field. You can imagine it like parallel, perpendicular, or antiparallel. I mean, I can tell you that there are other nuclei for which you have more than three orientations. And then the concept of orientation and direction of the orientation becomes like unclear, and then you really see how to say, picture like for children, this concept is, that we associate this with orientation. However, the story starts with the fact how magnetic moments of specific nuclei behave in a magnetic field. If they have only two possible orientation, the spin quantum number associated with this nucleus, and you will study NMR, you will see this word very often, is 1/2. In case there are three possible orientations, the spin quantum number is 1. Actually, the spin quantum number can be up to 9/2, but whatever, at this moment. Why it is so? You attach spin quantum number, for instance, 1/2, to an object. All the protons have spin 1/2. This is like fundamental rule of nature, and actually hydrogen nuclei are just protons. And what is happening? Alongside with the so-called spin quantum number, there is something, we do not need to know it, but it's useful somehow, that you are able to read something about NMR. There is something what is called magnetic quantum number. And the magnetic quantum number, there are several magnetic quantum numbers. They range from the spin quantum number to minus the spin quantum number. So if the spin quantum number is 1/2, the so-called magnetic quantum number can change between 1/2 and minus 1/2. But here is the trick. It can change only by 1. So it can be 1/2 or minus 1/2. Therefore, the magnetic quantum number can be considered as a quantity which characterizes the orientation in the magnetic field. Parallel, 1/2. Antiparallel, minus 1/2. In a kind of naive picture. Then if you have three possible orientations, then, well, it fits to the concept that the spin quantum number is 1. Because then it can vary between 1 and minus 1. And as the interval is 1, it can be 1, 0, and minus 1. Three possible orientations. So if you hear about spin quantum number, just so you are not surprised, there is a quantity which is intrinsically related with the magnetic moment. So here you have point 3. The magnetic moment is proportional to the spin. Yes. But the proportionality factor is called gyromagnetic ratio or gyromagnetic factor. So here we also must understand the concept of proportionality, that quantity y is proportional to quantity x if y is equal k times x when k is the proportionality factor. It means x changes twice, y changes k times 2, and so on, yeah? It's just linear function, the concept of proportionality. Something is proportional to something. I don't know how to put it in other words. It's like, what does it mean that something is proportional to something? You, for instance, you are told that, I don't know, your salary is proportional to the number of hours which you work, which is like quite a reasonable thing, yeah? Assuming that one works in this way, yeah? So then, if you work twice longer, you should get twice more money, yeah? If you work 10 times longer, you should get 10 times more money. Now, of course, so this is obvious. Now is the question how much money you will get, yeah? And it depends on your salary. Because it can happen that you and your colleague will work the same time, but one of you will get less salary, yeah? Less total amount because it's the matter how much you are paid per hour. It can also happen that somebody will work longer, however, get less total salary for the same reason, yeah? So although the magnetic moment is proportional to the spin, there's this proportionality factor, which is called geomagnetic factor. And this is like the salary per hour, yeah? So the magnetic moment is the geomagnetic factor times the spin. In the same way as your total salary is your salary per hour times the number of hours. It's just this full analogy. Let's assume that you have 3 persons, yeah? 2 of them work 10 hours, 1 of them works 15 hours. Point. Then they have salaries. Everyone has a different salary, yeah? So all possible combinations will apply when it happens to the total salary. Because in which case you multiply the number of hours by the hour salary of this person, yeah? And all possible interplay can happen. Somebody works shorter, gets less money. Somebody works longer, gets still less money than another person, and so on, yeah? So the same is here. To specify the magnetic moment, you take the spin, which is associated with the nucleus, multiply by the geomagnetic factor, which is also associated with the nucleus. There are tables of this. And actually, hydrogen atoms, protons, have very low spin, 1/2, the lowest possible, but at the same time they have very large magnetic factors, the largest one between all possible nuclei. So they create the largest magnetic moment, despite the fact that the spin is small. It's like the case. Somebody works only 5 hours but has so high salary, so it beats those guys who work 10 and 15 hours, yeah? This is perfectly possible. So the same is happening here. So this is what I'm trying to say, that the geomagnetic factor is an extremely important quantity because it determines the magnetic moment. And consequently, it determines the strength of the dipole-dipole interactions with other magnetic moments, with other protons, other nuclei. And it also determines the strength between this magnetic moment and the external magnetic field. The strength of the coupling, in other words, the energy of this interaction. Larger geomagnetic factor means larger magnetic moment. This means stronger interactions between each other, like for instance, two protons in water molecule, and stronger interaction with the external magnetic field. And this is the last thing eventually which I wanted to tell you. I told you at the beginning that when you apply higher magnetic field, the difference between the populations of those two energy levels, let us stay with those two, so spin 1/2, is larger. And I make the comparison between sitting and staying, or how to say, always sitting, but in less or more comfortable positions, yeah? The same thing is happening here. The geomagnetic factors determines also the energy levels, which correspond to the parallel and anti-parallel orientation, because as I said, it determines the strength of the coupling between the magnetic moment and the external magnetic field. So as it determines the strength of this coupling, it also is the same word, actually the same statement. It determines the energies of those interactions, yeah? As those energies are larger, also the difference between those two energies are larger. So the gap between those two energy levels is larger. So if I take, for instance, carbon-13 and 1H, and both of them have spin 1/2, and I apply the same magnetic field, the gap between the two energy levels, corresponding to the parallel and anti-parallel orientation, will be larger for 1H because of the geomagnetic factor. So the message is that not only the spin itself determines the gap of energy, because you will find several nuclei will have the same spin quantum number, and this only means what orientations, how many orientations they can take in magnetic field. But the real difference between the energies associated with those two orientations are determined not only by the spin, which can be the same, like in this case 1/2 for both of them, but also, and first of all, of the geomagnetic factor, which you can look up and see what values they take. And you will see that for 1H is the highest one. And then is the last thing, and I think we should stop at that moment. When you perform experiments, you hear like using this our so-called time domain, forget this term, we operate at 20 megahertz, more or less. We are proud that using fast field cycling relaxometry, we can cover broad range of magnetic fields from, let's say, 10 kilohertz to 20 megahertz. You hear that, somebody has, I don't know, somebody has spectrometer which operates at 600 megahertz. And somebody is very proud because got a magnetic resonance system operating at, I don't know, 800 megahertz. Yeah. This is something what we'll hear commonly in the world. The first thing, you must understand what hertz is. It's a very simple thing, it's 1/2. So the concept of frequency, to understand it is absolutely necessary, but this is, the concept of pendulum. period and frequency. And actually, even applying this to life sciences, this is like, what is the frequency of acoustic wave which you are able to hear? What is the frequency of electromagnetic wave which you are able to see? Everything is about, life. Second, one absolutely must know what kilo, mega, and so on means. This is also something to look up. We may not struggle with units. It's like, everybody knows that 1 meter is 100 centimeters, and 1 centimeter has 10 millimeters. Consequently, 1 meter has 1,000 millimeters, and so on and so on. One must understand the concept of units and the meaning. One must understand that kilohertz is 1,000 hertz, megahertz is million hertz, consequently megahertz is 1,000 kilohertz, and so on. Yeah? Then, what is the point? The energy difference between those two energy levels can be expressed in hertz. Why? Well, at this moment, I can ask you what are the energy units. Yeah? You can say that this is joule, for instance. Maybe this is the unit of energy which you will answer. One can express energy in hertz, in frequency units. It means in hertz. I do not want to refer again to quantum physics and Pauli law. However, electromagnetic waves have certain energy, yeah? So you can ask yourself, what will be the frequency of electromagnetic wave which would have the energy which I'm dealing with? In this way, you can express the energy gap in hertz. And as we agreed that the energy gap depends on the magnetic field and depends on the zero-magnetic factor, it's worth to remember that for protons, it means for hydrogen atoms nuclei, if you apply magnetic field 1 Tesla, the gap between the two energy levels will be 42 megahertz in a good approximation. And when you perform your experiment, this what you have on the x-axis and this what we change is actually the frequency. The gap between the two energy levels expressed in frequency units, and this frequency is called resonance frequency. So we, for instance, write 1H resonance frequency. It's important that it is for 1H because it depends on the zero-magnetic factor. You can apply the same magnetic field, but get completely different resonance frequency because it depends on the spin and the zero-magnetic factor. Yeah? In this case, yeah. So this is what the concept of resonance frequency comes from. So this means that what we are doing, we are not by any magic change resonance frequency in a direct sense. What we do, we change the magnetic field. And the magnetic field determines the resonance frequency. So in principle, there are, some traditions and well-established ways of present data. However, in principle, one could also plot the relaxation rate, reciprocal relaxation times, versus magnetic field. The ratio is 1 Tesla is equal to 42 megahertz. However, this is what the resonance frequency comes from. As it took us more than 1.5 hours, I would propose that I do such a thing. I stop sharing, then I stop recording,